We're continuing with section 8.2.1, and we're starting with problem 8-38. Before you start that problem, I'd like to remind you of the commutative property of multiplication. The commutative property of multiplication means that it doesn't matter where you move around the numbers to. It doesn't matter what order you put the numbers in. And a good way to think of that is commutative is very similar to the word commuter. A commuter is a person that has to travel from their home to get to their work. With the commutative property of multiplication, it doesn't matter where the numbers are. They can still do their job. So if you multiply 3 times 2 times 3, and then if you change the order of these numbers so that you're multiplying the 2 first, 2 times 3, that really doesn't matter to the end product. So 3 times 2 is 6. 6 times 3 is 18. 2 times 3 is 6. 6 times 3 is 18. So in both cases, even though the numbers are not in the same order, the end result, the product, is the same. You're going to be exploring that as you answer problem A. Go ahead and work on problem A, and then come back to me in a moment after you've completed that. All right, they're asking you to check and see that 2 times 10 is equal to 10 times 2. And then they ask you, is it also true that 2 divided by 10 is equal to 10 divided by 2? Well, we know 2 times 10 is equal to 20. And we know that 10 times 2 is also equal to 20. Is it also true that 2 divided by 10 is equal to 10 divided by 2? Well, 2 divided by 10 is equal to 0.2. If we divide 10 by 2, that's equal to 5. So even though 2 times 10 is equal to 10 times 2, they both are equal to 20. It is not true with division. So there is no commutative property of division. There's only a commutative property of multiplication. These are not the same. Order does matter when you're dividing. Now they'd like you to factor this. So go ahead and work on that, and then I'll come and work on the second part, and then we'll rejoin you. Okay, write the expression 5 to the second power x to the fourth power times 5 to the x, or 5 times x, in factored form. So 5 to the second power is 5 times 5. X to the fourth power is x times itself 4 times, x times x times x times x. And 5 times x is just 5 times x. So there it is in factored form. Now you're supposed to explain, how does the commutative property help you simplify the expression that you just, well, I was going to say the one you just factored, but no. So if we were to simplify, to simplify the expression to equal 5 to the third power x to the fifth power. Well, it's easier to count things up if they're all in the same place. So you've got 3 5s, 5 times 5 times 5, and you've got 5 x's, so x times x times x times x times x. So when they're together, it's really easy to see that this expression here is equal to this expression, because 5 multiplied times itself 3 times is 5 to the third power, and x multiplied times itself 5 times is x to the fifth power. So the commutative property just helps you organize something that may look a little messy. You can switch all the numbers around so that they are in the same place, and then it's easy to count them up. So that's how the commutative property can help you simplify the expression up here to be the expression over here. All right, now go ahead and do this part of the problem. Put me on pause and I'll rejoin you. So if we were looking at this problem and we wanted to write it in simplified form, we can do it two ways. We can either, we can use the rules that we created on the first page, where we know that we can just, if the base is the same, we can just add the exponents, or we can factor out the whole thing. So let's do it both ways. So here we've got 3 to the first power, because there's just one 3. We've got another 3, another 3, and another 3. So really we have 4 3's. So we could write that as 3 to the fourth power. Then we've got w to the third power, w to the second power, and just plain w, or w to the first power. So if we added 3 and 2, we'd get 5. If we added one more, we'd get 6. So that would be w to the sixth power. Now we don't usually leave numbers in their exponent form, so 3 times 3 is 9. And 3 times 3 is also 9. And then we can multiply those two 9's together, and we'd get 81. So 3 to the fourth power is 81. And then w to the sixth power. So this is the final simplified form of that. That was the shortcut way of doing it. So now let's factor it out and see what we get. So 3 times w times w times w. We've got w to the third power right there. And then times 3. And then times w to the second power, w times w, times 3. And then we have just one w. And then a final times 3. So if we count up our 3's, 1, 2, 3, 4, we've got 3 to the fourth power. And count up our w's, 1, 2, 3, 4, 5, 6 w's, w to the sixth power. So either way, we end up with the same answer. And of course, we know 3 to the fourth power is really 81. And we'll put that next to w to the sixth power. Now turn your attention to 8-39. These are numbers that are all multiplied by 10. And as they observe here, multiplying a number by 10 changes the number in a special way. So we're going to simplify each of these without using a calculator. You're going to use your ingenuity to figure out how to multiply these numbers without a calculator. I'll rejoin you in just a moment. All right, so you worked on this problem and you looked at A first, 9.23 times 10. So you're multiplying this number times 10, and because of that, 10 is what each place value is worth. And so we know that we're increasing this whole number by one place value. So we do that just by moving the decimal point back one place. So if we're multiplying 9.23 by 10, we're really making that number bigger. So we know that we're going to end up with a bigger number, and we do. It's 92.3. If we multiply this number, 9.23, by 10 to the second power, we know that 10 to the second power is really 100. So we're multiplying this by 100. And basically, we know that we're going to be increasing 9.23 by 2 place values. So if we move the decimal point back, we're increasing this number, we're making it bigger. So we get 923. So here, 9.23 is now being multiplied by 10 to the third power. So 10 to the third power is really 1,000. So we're going to be making this number bigger by 3 place values this time. So 9.23 becomes 9, 2, 3, and then to get the next place value, we're going to have to add a 0. So now we've increased this number by 3 place values by multiplying it by 1,000, or 10 to the third power. So I'm sure you're noticing a few patterns here. We've got 2 zeros on 100, and this is 10 to the second power. We've got 3 zeros and 1,000, and we have 10 to the third power. Let's see if that pattern holds. So here we're multiplying it by 10 to the fourth power. 10 to the fourth power would be 10,000. So we've got 4 place values now. We're going to be increasing this number to be bigger by 4 place values. So if we make this bigger by 4 place values, we're really going 1, 2, we have to add another 0 to make it 3 place values, and then we'll have to add another 0 to increase it by 4 place values. So we've increased it to this value by 4 place values, and it was 10 to the fourth power. So go ahead and think about the patterns that you see in this problem, and then based on those patterns, answer A in 8-40. I'll rejoin you in just a moment. Based on those patterns, what do you think 9.23 times 10 to the seventh power would be, and why? If we follow the same pattern that we noticed here, we know that this is going to increase 9.23 by 7 place values. So we're going to have to move that decimal point back so that this number gets bigger and bigger and bigger. If we write out 923, and we know that the decimal point was originally here, so we need to increase it by 7 place values. 1, 2, 3, we'll add a 0. 4, we'll add another 0. 5, another 0. 6, another 0, and 7. So there's our last 0, and we can put our decimal point. So what does this number look like now? There's our first 3 zeros and our second 3 zeros. So it's 92,300,000. Why is this correct? Well, we noticed that it would increase by 7 place values. So the exponent is 7 place values. So it increased by 7 place values. So look at these patterns again and try to find the product for each of these without using a calculator. I'll rejoin you in just a minute. We're going to use the same patterns that we noticed here and here to figure out what this looks like if we express it if we simplify it. So we notice that this is 10 to the second power. So that 2 we know means that we're going to be looking at 2 place values. If the decimal point is here now and we're multiplying it to increase it, we know that the decimal is going to have to go back so that the number that we have in the end is a bigger number than 78. If we move this back 2 spaces, it'll end up between the 5 and the 9. So 10 to the second power times 78.659 will end up being 7865. Then we'll put the decimal point, and there we have our final number. If we look at this number, 10 to the 5th power, so that's going to increase this number by 5 place values. So we can write out the number like this, and we'll start the decimal place here. 1, 2, we've gone 2 places. 3, we need to add a 0. 4, we need to add a 0. 5, another 0. So there's our final number, 34,638,000. Take a look at this last problem, and I will rejoin you in just a moment. All right, so we're supposed to write a statement here describing how we can quickly multiply by powers of 10. So we might want to include information about how the decimal point moves after multiplying it by a power of 10, and maybe why we have to add zeros. Okay, so why does this pattern work? Well, we know that each exponent increases our number by 1 place value. So that's one thing that we can write. The exponent represents the number of place values. So an exponent of 5 increases the value of a number by 5 place values. All right, and sometimes we need to add zeros because we need to show the increased value of the number. Sometimes we add zeros to make a number bigger. Or show more place values. That's my explanation, but you may have expressed this differently, and that's okay too. In fact, maybe you found a better way of saying this.